Welcome to Aerodynamics number 89, and today we're talking about the WindEEE, which is a wind tunnel that is designed to simulate storm fronts, so the weather patterns, so like the flow. And to do that, we're going to look at a paper called Downburst-like Experimental Impinging Jet Measurements at the WindEEE Dome. This is open access, so you can find it in a link in the description. And this is not the first time we've been looking at wind tunnels like this. The first time we looked at this was in podcast number 3, so almost a year ago. We were looking at another wind tunnel. You can look at that podcast as well. These two wind tunnels are a little bit different though. That one had a very similar construction to a regular wind tunnel, and they used something called louveters, which are these little flaps that open and close to simulate an impinging jet. So there's flow coming down and hitting the ground. This one is a much bigger wind tunnel, and it produces more of a radial front, which is much closer to what a storm actually does. So we'll go through that in this podcast. So if you want to check out the other podcast, number 3, you can check that out as well if you want to listen to a younger version of me too. So let's get started. Downbursts are strong buoyancy-driven downdrafts of cold air that descend from thunderstorm clouds. Once the downdraft hits the surface, the velocities in the radially advancing outflow can exceed 75 meters per second in the first approximately 100 to 150 meters from the surface, whereas the maximum flow intensities occur and give rise to the well-known nose-like shape velocity profile. So let's talk about what this means. When you have thunderstorms, as you have these clouds, you often have it's very variability in what the air is doing, and often you can get these massive pockets of air rushing down into the ground, vertically down. And what happens is this air hits the ground and it has nowhere else to go other than just radially out. And what happens is the flow accelerates, like it hits the ground and then accelerates outwards. And they can reach up to 75 meter per second velocities at 100 to 150 meters above the surface. And they talked about what's called a nose-like shape profile for the velocity. And this can be kind of thought as like a boundary layer profile. If you were to stand on the ground away from this impinging jet and you took a cross section and you looked at the velocity of the flow as you go up from the ground, what you get is the velocity increases as you go higher, and then it gets to a point where it then starts decreasing. So like there's this bulge pattern, and this is what they call the nose-like shape profile. And this is what they're talking about. This is why they say that at 100 to 150 meters from the surface high, these velocities can be 75 meters per second or higher or greater. Whereas when you go above that, then they start to decelerate a little bit. And when you're below that, there's a little bit less as well. This is the nose-like shape profile. So the outflow is led by the primary vortex, which is a vortex ring that forms below the thunderstorm's parent cloud because of the instability between the dense cold column of air descending to the ground and the calm surrounding environment. Figure 1a represents the schematic of the downburst spatial evolution. The high wind speeds near the ground compose a serious threat to structures, aircraft, and the environment. So let's look at figure 1. So they have, for those of you listening to this, you can watch it on our YouTube channel, or you can also look at the video on Spotify. I'm quite certain you can get it there. What happens is the air coming down is cold, and because it's colder, it sinks and it hits the ground. And then you get this ring vortex forming. And the ring vortex, if you were to take a cross-sectional cut, on the left, it has a clockwise motion. On the right, it has a counterclockwise motion. So it's like trying to escape the ground effectively. They say, on average, downbursts last for approximately 10 minutes, and their spatial extent is not larger than several kilometers in diameter. This makes downbursts small scale, highly three-dimensional, and unsteady wind flows. Consequently, real measurements of downburst winds in nature are very challenging and still rare compared to the larger scale wind flows associated with atmospheric fronts and low pressure systems. This lack of data and complexity of downbursts often make it impossible to reconstruct the overall spatial structure of this phenomenon by only relying on the standard anemometric records. In parallel to the field measurements, downbursts have been investigated computationally. However, numerical models often lack the proper representation of turbulence and instabilities, mainly due to coarse spatial and time resolutions used in the discretization process of the governing equations. What's more, the numerical approaches often have a lack of validation data because, first of all, the real-life validation data is sparse. Secondly, the wind tunnel validation data is also somewhat sparse in the sense that it's not entirely accurate compared to the real life events, because often wind tunnels are on a much smaller scale. So there are some peculiarities that occur in podcast number 3. Actually, we cover some of these, but I won't go through them here. We'll cover some other differences here. So for these reasons, the physical modeling of downburst winds in experimental facilities has played an increasingly more important role through the last decades. Two experimental approaches to create downburst-like flows in wind simulators are buoyancy-driven currents and momentum-driven impinging jets. The velocity scale of gravity current experiments reported in the literature is often too small to facilitate reliable measurements of the kinematic properties of the near-ground wind field, which, however, is the layer of interest in the study of flow structure interactions. In other words, the first way of producing these impinging jets, of these downbursts, are buoyancy-driven currents. And this just means when you have differences in buoyancy of different pockets of air. The problem with our current wind tunnels with this is that they usually are too small. The second way, momentum-driven impinging jets, is far more common, and that's because they do produce better results in terms of the nose shape profile, as I was saying. So, nevertheless, the facilities that are capable of creating downburst-like impinging jets are still few and sometimes limited by small scale or, for instance, continuous impingement of the jet that creates a 3D but steady state outflow near the surface. So this is still one problem because you have to have such a big wind tunnel to produce similar timescales. Currently, the largest geometric scales of experimentally produced impinging jet downbursts are achieved in the Wind Engineering Energy Environment WindEEE dome at the Western University in Canada. This paper is focusing on. The reported geometric scales in their experiments are approximately 1 to 200 and better. So that's pretty decent. Other wind tunnels, they are on the order of 1 to thousands. So the WindEEE dome is a hexagonal chamber of 25 meters in diameter, surrounded by an outer return chamber of 40 meters in the diameter. So in podcast number 3, we go through some of this type of geometry, and you can, I'll explain it here again just briefly. So what we have is a massive room, and then in the middle of the room at the top, we have a nozzle. And this nozzle is where the air comes through. You're throwing air into the ground from above. And at the sides of the room, you have exits. And this is where the air can go through to get sucked back up and recycled. And this is how the wind tunnel actually operates. So this is quite amazing because a regular wind tunnel, as we know, we have like a closed loop system, and it's usually just like a long tube that goes around. This is a very different type of setup. So it's just cool how we can make different wind tunnels, and this is one of them. So the 25-meter diameter testing chamber has 100 fans on the peripheral walls, out of which 60 are mounted on one of the 6 walls in a matrix of 4 rows and 15 columns. The rest of the 40 fans are distributed at the base of the other 5 peripheral walls. The upper plenum, with 6 large fans, is situated above the testing chamber. So the plenum is just like the big opening above the room, which is where the air goes, and then it comes back in. The test chamber and the upper plenum are connected through a bell mouth situated at the ceiling level of the test chamber. So that's where the nozzle is, what I'm talking about. And figure 1B is the photograph of the WindEEE dome testing chamber. And it's very big. It's a 25-meter diameter room, so that's a massive wind tunnel. In this paper, a large database of measurements recorded during a recent experimental campaign in the WindEEE dome is presented in terms of the methodology, instrumentation, and specification of the spatio-temporal grid of measurement points. In the following of this paper, their experimental data are validated against a real downburst in order to estimate the accuracy and applicability of the experimental method to replicate these types of wind events. So let's talk about their facility. In the WindEEE dome, downbursts are simulated as pulsed impinging jets through the rapid opening and closing of mechanical louvers, as I mentioned earlier with podcast number 11 when I was talking about that wind tunnel. They use a similar sort of mechanism. And these mechanical louvers, these shutters, are open and closed rapidly, and they're stored just above the nozzle. And this results in an impinging jet that runs through the bell mouth, through the nozzle, before impinging on the floor of the test chamber, so directly downwards. The process of creating a transient impinging jet has 2 steps. First, the upper chamber is pressurized using the upper fans, so those big 6 fans that we mentioned earlier. And by closing the louveters on the bell mouth, so in other words, you have these big 6 fans pushing all this air into a closed surface, effectively. Second, once the pressure reaches the desired pressure of approximately 3.4 hectopascals, sorry, so 3,400 pascals, sorry, 340 pascals, I mean, above the pressure value in the test chamber, the louveters, the shutters, then open and the air is released into the test chamber. So we have this big rush of air. The diameter of the bell mouth can vary from the maximum value of 4.5 meters to a minimum of 1.2 meters. And in this study, 3.2-meter diameter was used. In the present experiments, investigated 2 different intensities of the impinging jet, and they were determined using the centerline jet velocities at the exit of the bell mouth. So in other words, how fast the air is coming up. The corresponding velocities were 8.9 and 16.4 meters per second. Hence, these 2 cases are now referred to as dB 8.9 and dB 16.4. And figure 2 shows this setup in a schematic. So the wind tunnel itself, the big room that it's in, is hexagonal, as we mentioned, and the air goes down, gets sucked out by those fans around the walls. The air then goes back up to the top and then gets pushed back into the nozzle. So in figure 3, we're looking at the velocity measurement setup, first, and we'll get to figure 3 in a second. So Cobra probes are used here. So they are multi-hole pressure probes designed to resolve 3 components of velocity in real time. So Cobra probes are pretty cool. I'll explain what these are briefly. I've touched on them before in the podcast. So they're multi-hole pressure probes, and multi-hole pressure probes is a big family of probes. What this is effectively, if you have a pen next to you, let's say, just pick up your pen and look at the blunt end of it. Now imagine that there are a bunch of holes in the front. That's what a multi-hole pressure probe effectively is. And the reason why we have holes here is because each hole will, when you put it into the flow, will register a different pressure. And this pressure can then be calibrated. We calibrate the probe so we know when a pressure, let's say the pressure in hole number 1 is X, hole number 2 is Y, hole number 3 is Z, then we can figure out, okay, well then the velocity is this. And we can figure out the 3 different components of velocity. That's what a multi-hole pressure probe is. Now, multi-hole pressure probes can range from 4 holes, which is actually a cutting-edge design, which I'll talk about in a second, ranging all the way up to, I don't know what the maximum is, but I was talking to someone a few years ago, and they were saying that his research group, they were looking at 21 hole pressure probes. So that means that they have 21 holes scattered around the entire probe. So what is the benefit of more holes? The benefit of more holes is that you can measure a greater radius. So with a Cobra probe, which only has 4 holes, you can measure the flow within a 45-degree cone of the axis that you're pointing in. So that's very good if your flow is within 45 degrees of the center axis. But if the flow is outside that, you need more holes to then be able to measure those pressures. That's where a multi-hole pressure probe with more than 4 holes comes into it. Now, there is a limitation to this, though. If you have the shaft of the probe, that interferes with the flow. So if you have holes right at the back of on the rear face of the probe, the shaft of the probe is going to interfere with these readings, which means you can't get a full 360-degree reading pattern. Usually you can only go up to about 300, 320 degrees maybe, which is the limiting factor, not the number of holes. So that's what multi-hole pressure probes are. Cobra probes, the reason why they are groundbreaking, and they're not new, they're quite old, they're from the 70s or so, they are deal. They come from a guy called Elaine Crew. And the reason why they are so revolutionary is because they use only 4 holes. So before Cobra probes came around, 5 holes were the minimum they could use to get your velocity readings. Then this guy, Elaine Crew, he came up with a mathematical approach to be able to get the same readings with only 4 holes. And you might say, well, what's the big deal? It's only 1 hole. Well, the big deal is that you can make a probe which is smaller. And that is a big deal in terms of reducing the amount of interference to the flow. So if you want to have more holes, typically the probe gets bigger, and because you just need to accommodate these holes, and that means that you disturb the flow more. And also the point that you're measuring is no longer a discrete point. You're now measuring over an actual area or a volume. So the bigger the probe, the bigger the area that you're measuring over. So you can't really say that the flow at this point is whatever velocity, you have to say the flow in this area is this velocity, generally speaking. So there's some error occurring there. So having a smaller probe is very beneficial from that point of view. Another point of view is to get the frequency response. So if you have an unsteady flow, it means that the flow is changing in velocity with time. And all flows have this to some extent. We call this determined intensity level, typically speaking. However, it could just be unsteadiness in general. And if you want to measure this, you want to measure the unsteady component. And to do that, you need to have fairly big holes. The reason why is because the smaller the holes, the longer it takes for the air, and also there's damping involved, for these pressure fluctuations to make it through the tubing to the sensor. And we don't want that. We want to have as quick as possible the response. So we want to have bigger holes. So if we have a 4-hole probe compared to a 5-hole probe, we can even use the same size probe. We just make the holes bigger, which means we can get a greater frequency response, which means we can measure unsteadiness better. So that is one of the big deals for Cobra probes. Now, let's move on to we'll talk about Cobra probes in a little bit again, but let's move on to their setup now. So in figure 3, the experimental setup is given. The flow was measured at different radial positions around the center of the jet using these Cobra probes mounted on a heavy and stiff mast that prevents vibrations of the probes in the flow. So this is important when you're looking at the frequency response, because if you have the mast vibrating around, that's going to introduce this frequency into your readings. Now, if you want to look at the steady state stuff, so you average everything out, that's not a big deal, unless you have changes in turbulence and blah, blah, blah. But generally speaking, it's not a big deal. But if you want to look at the unsteadiness of the flow, you don't want to have frequencies being corrupted by shaking. And I actually recognized this mast from a company that is based in Canada. I won't go into who they're made by, but yeah, they make some pretty decent stuff with these masts, and they have 7 Cobra probes lined up here. So the height of the probes of the mast on the masts ranged from 4 centimeters to 50 centimeters above the test chamber, and now distributed along this range here. For every radial position, each impinging jet experiment was the same initial conditions, and they're with the same initial conditions, they were repeated 20 times to inspect the repeatability of the tests and to build more statistical significance of the results, including the analysis of the variability. So repeating a experiment is important in this particular case because they're looking at the unsteadiness. They want to see if we can repeat the same flow every time. But also, if you repeat an experiment, you can reduce the amount of error. So if you take an experiment and you do it once, and let's say you're measuring the force, and you get the force is 5 newtons, and you have done a error analysis of your load cell or whatever you're using, and you know that it's 1% plus or minus the uncertainty. If you then do another 3 measurements, you can then drop that random error by a factor of 2. So you can halve that because it's the square root of 4, which is the measurements that you've taken. If you do 9 measurements, the square root of 9, which is 3. So you can drop that uncertainty by a factor of 3. So doing more measurements is good from that point of view. The downside of that is that you are using more resources. So in this paper, their number of measurements that they did were 2 jet velocities by 20 repetitions by 10 radial locations, so distance around the center, with 7 probes resulting in 2,800 velocity records. So that's quite a lot. They're effectively doing a weight survey here with different probes. Now, let's go back to the Cobra probes. The reported manufacturers actually of these probes is plus or minus 0.5 meters per second in the velocity measurements, with a plus or minus 1 degree yaw and pitch angles up to 30% terms intensity. So that's very good. The sampling frequency of all velocity measurements were 2,500 hertz, which is sufficiently high for measuring turbulent flows. So this is true for turbulent flows. If you want to look at noise, you need to go even higher because 2,500 hertz is not a very high-pitched noise. But for turbulent flows, Cobra probes are good. In terms of the frequency response, this is actually quite high because the early versions of the Cobra probe, which I've also used, the early versions and these new versions, the early ones, they were limited to 500 hertz. So in recent times, the Cobra probe manufacturers, which come from turbulent flow instruments, I think they're called TFI from memory, they have really increased the the resolution of their frequency a lot. It's quite nice. So there's another note that I want to mention here. During the testing, the air temperature and air density in the chambers were approximately 296 Kelvin and 1.148 kilograms per meter cubed. That's right, I said 1.148 kilograms per meter cubed. If you're listening to this and you thought, well, the density of air is 1.2 or 1.225 kilograms per meter cubed, that's just an average, and it's not right pretty much any day. Every day it's different. And what these people have done is that they've measured the density of air, which is a good thing to do if you're doing experiments. And if you're doing experiments to get validation data for your CFD, you should also measure the density of air because it affects the density that you use in your CFD. And if you have the wrong density, you're going to have the wrong validation going on. So these people, they measure the density. It's very good. And the reason why I mentioned you should measure the density is because also we make the Atmosphere Hawk, sorry, that's another instrument, and it actually measures the density of air for you. So if you're doing experiments or you're getting experimental data to validate your CFD, you need to get this instrument to measure the density so that you have a much more accurate data set. The density of air changes by about 2 to 4% every day, and even more between seasons and years. So 5 to 10%, and even 15% is quite common between seasons. And the Atmosphere Hawk, gets rid of that error for you. So you can find that in the link in the description. So let's talk about the data synchronization. So data synchronization from 20 repetitions, were performed using a time-dependent spectral analysis of the time series. So why do we need to do this lining up of the different data series? Well, what happens is they have these Cobra probes at these different locations, and they have the jet impinging down on the ground. And let's say you have the shutters closed, the louveters closed. The air is building up. Then all of a sudden, you open the shutters. Now the air is going to rush through and hit the ground and then go radially out. So you want to, every time you measure this, you want to line up all your data series so that they align properly so you can look at what's happening with the flow in time. And this is potentially a difficult thing because if your wind tunnel is not repeatable, then trying to line up these runs is going to be much more difficult. To get around that, they looked at something called the frequency response. So they looked at the time series, first of all, with the data, and they aligned them, then looked at the frequencies that they were occurring with something called a power spectral density analysis. So the power spectral density analysis is kind of what it sounds like. With time, you're looking at how much power you have at each frequency. And this is very common for aeroacoustics, but also here with the thermostensities as well. So in figure 4, they depict this methodology, and figure 4A and figure 4D show time series of the radial wind speed and the corresponding moving average valued over a time window of 500 samples for repetitions 0, for repetitions 9, and repetition 20. Figure 4B and E are the periodogram power spectral densities of the velocity records calculated using 22 to the power of 7 points in segmented windows. So what this means is you're just looking at the power spectral densities using a certain number of points. I don't want to get into the details here because I have a lot of details here talking about how they calculated this. Just briefly, it's quite standard in terms of how they're using it with MATLAB. They're using something called a Hamming window with a 50% overlap, which is very normal. So finally, they talk about the technical validation of their measurements because at the end of the day, they want to use this experimental research so that not only they can validate their WindEEE dome being a good analogy to what happens in real life, but also for other experimenters and CFDers to use this data to help them too. So let's go through. So the technical validation. The technical validation of the experimental campaign presented in this article can be assessed through 3 levels: the Cobra probe interpretation, the wind tunnel test, and specifically the WindEEE dome laboratory. So in the measurement instruments, they talk about the Cobra probes. Were they a good pick for this type of research? So they say Cobra probes are robust, flexible, and easy to mount velocity measuring devices widely used in wind tunnel applications. Cobra probes are able to resolve unsteady velocity components because their pressure transducers are located in the close proximity to their pressure sensing ports. So let's talk about this. Another benefit of Cobra probes is that it's an entire unit together. So you have the front of the probe, that's where the holes are. Then you have the tubing going from the holes to the unit itself. And in the unit, you have the pressure sensors. The entire thing itself is only like about 15 centimeters long, maybe a little bit less. And the core part where the pressure sensors are is only like a diameter of 1 centimeter. This is different to a lot of other pressure probes because often you have the probe itself and then you have the pressure sensors located like 5 meters away. The problem with this is that the longer the tubing, the lower the frequency response you get out of your setup, because there's damping associated with the movement of air going through this tube, and also depending on how the diameter of the inner tubing is, the inner diameter. The greater this diameter, the greater the frequency response is, because damping reduces. But with Cobra probes, because it's so compact, you can get a high frequency response, which is a very good thing. However, there are other instruments that can do a similar thing, such as hot wires, but are they good in this situation? So Gu and Wood compared the Cobra probes against hot wire anemometers and demonstrated their capability to measure mean and fluctuating components of the velocity field in high turbulent environments. So in terms of densities above 35%. Some advantages of Cobra probes over hot wires are their robustness, temperature insensitivity, ease of use, ability to withstand moderate NOx and contaminated flow. So let's go through each one of these. Robustness, compared to hot wires, Cobra probes are very robust. Hot wires, if you look at them wrong, they'll break. They have other things called, Dantec came up with a new one, which has a much thicker wire. It's like 100 times thicker, I think, something like that. Their frequency response is a little bit lower, but they're much stronger, but you can't really fix them yourself. Although they do sell replacements, and you can sort of solder them on if you know what you're doing, but it is quite fiddly. Whereas with hot wires, they're far easier to fix with the traditional filament. Regardless, both of them are still far weaker than a Cobra probe, and that means you can't really knock them, and you can't even look at them sideways. Cobra probes, they're temperature insensitive, whereas hot wires, they rely on the temperature. That is true. When you're looking at turbulent flows, though, that's not necessarily a big limitation, because the response of a hot wire with turbulence intensity becomes linear above a certain velocity range. So that means that even if you do have a drop in temperature, it's all linear, and that doesn't affect the results that much. In fact, a lot of aeroacoustic measurements done throughout the decades have actually been done without calibrating hot wire at all, because the linear range is what we're looking at. Do I recommend that? No, you should calibrate your instruments, but there are, I would say, the majority of papers that I've looked at, and I have some friends in aeroacoustics, they say the same thing. They don't calibrate their hot wires. They just put them in. It doesn't matter what the temperature is, doesn't matter what their frequency is, their response is at the low end of velocities, because at high end velocities, like let's say above 5 meters per second, the response is linear. So that's potentially a limitation of hot wires depending on the velocity of the flow, but not necessarily. Ease of use. Cobra probes are much easier to use than hot wires when you're talking about calibration. Apart from that, they're about the same. However, Cobra probes, some disadvantages of Cobra probes and probes in general compared to hot wires is that they are much bigger. You can't usually put them in the boundary layers because their spatial resolution is so much worse. Hot wires are much smaller, so that means that you can get them into the boundary layer, and you can measure different turbulent patterns in the boundary layer compared to hot wires, compared to Cobra probes, sorry. So a very large number of wind tunnel engineering experiments in the literature have used Cobra probes, which is fine. Cobra probes are quite nice. However, there are other instruments that you can use, such as hot wires, if you know what you're doing. So the wind tunnel experimentation, let's talk about this, the validation of it. So the wind tunnel tests are divided into two main subcategories. The first includes tests in the mechanical and aeronautical field to assess the aerodynamics of vehicles and aircrafts. The second category includes tests in the civilian environmental area to simulate and study various flow fields, transport and circulation of passive substances, and the investigation of wind actions and effects on the building environment. Let's talk about these two different main categories. So with the first category, this is the traditional type of wind tunnel that we're familiar with. This is an aeronautical wind tunnel. The second type is an environmental wind tunnel. Now, what is the difference? I've covered this in other podcasts previously. For example, in podcast number 39, I look at blockage ratios and I talk about different wind tunnels there. Number 45 podcast, I'm talking about contraction ratios, and again, I'll talk about different wind tunnels there. And you can listen to those if you like. Just in a nutshell, the aeronautical wind tunnels, they are typically have a far more uniform flow. So they differ in a few different aspects. The first one is that the turbulence density of aeronautical wind tunnels is typically far lower. It's in the order of 1% or less. Typically around 0.5% is average. If you can get it below 0.1%, then you're doing very nicely. Another major difference is that the aeronautical wind tunnels, they have very small boundary layers. And the reason why is because when you're thinking about the operation of things that are in aeronautical wind tunnels, for example, airplanes, we don't have boundary layers around the airplane. We just have them on the surface, but there's no like surface around. There's no like ground the airplane is flying through, which has a boundary layer. It's usually in the sky. So we don't want boundary layers there. Contrasting that to environmental wind tunnels, they typically have much higher turbulence densities and much greater boundary layers. These two things are for good reason. The first reason is that in close to the ground, if you go for a walk outside, for example, today, you'll feel that there are gusts, there are breezes, there are zephyrs, I might even say. And these are different turbulence densities. And that means that if you were to put a wind turbine or a building in an aeronautical wind tunnel, the turbulence density in that is far too low compared to the environment that it would typically be in. So that's where environmental wind tunnels come into it. We want to have a high turbulence density level to mimic what's happening in real life. Typically, they are about 5%, but it can go up to even 20%. Another major difference, I'm talking about the boundary layer. Again, if we think about what's happening on Earth, on the surface, we actually have a boundary layer forming. So when you walk around outside, you're in a boundary layer. And the reason why that is because if you think about a wind coming along, it's going across the ground and there's a boundary layer forming. It's very big. Typically, the boundary layers of over the surface of the Earth is like on the order of like 100 meters tall. They're very big. Even more if you think about the free stream velocity is actually where you get like kilometers above the surface. And you can argue that the boundary layer has been greater than that. But even still, the boundary layers are massive on the surface of the ground. So we want to have this same kind of thing happening in our environmental wind tunnels. We want our wind turbines, for example, or we want our buildings to be in a boundary layer because that's what happens in real life. So we want these boundary layers forming. So how do you make these boundary layers form compared to the aeronautical wind tunnels? The main way that, there are two main ways that we can change the boundary layer profiles. The first way is with the contraction ratio. And again, in podcast number 45, I talk about this in detail. But the contraction ratio really affects how the boundary layer forms. And by changing that contraction ratio, we can either create like a aeronautical type wind tunnel or a environmental wind tunnel. In terms of the turbulence density level, again, contraction ratio does affect that, but also the conditioning of the flow. So the mesh screens that we have, the honeycombs that we have, etc. Typically in an aeronautical wind tunnel, we have many more mesh screens than in an environmental wind tunnel. And the honeycomb is typically much finer. And even to the point where in an environmental wind tunnel, we may not even have any meshes or even a honeycomb, depending on how rough you want the flow to be. Another major difference between these two wind tunnels is the blockage ratios that you can get away with. So for an aeronautical wind tunnel, we want the blockage ratio to be as little as possible because the flow is very sensitive to these blockage ratios. And in real life, we don't have any blockage ratio. When you think about an airplane flying around, there's nothing really constraining its flow going around it. So blockage ratios we want ideally to be 3% or less for aeronautical wind tunnels. If you get above 3% to about 5%, you can make corrections with that, but they're erroneous. Again, I've got another podcast on that. And then if you go above 5%, then the results pretty much become trash. People argue that you can use them, but I argue that you can't because the flow physics is completely wrong. Anyway, you want to have a blockage ratio as low as possible. And whereas with the wind tunnel engineering side of things, with the aeronautical engineering side of things, their wind tunnels, you can get a blockage ratio much higher, 10%, even 20% you can go up to, and the results are still usable. And the reason why that is because first of all, the flow physics doesn't change that much because often the flow physics going around is for a bluff body. Secondly, on their environment that you find wind turbines and buildings, for example, there are other things around constraining the flow. So there are often blockage ratio kind of features happening in real life. So you can get a higher blockage ratio in your wind tunnel if you like. So these are different types of wind tunnels and the differences. This wind tunnel that we have here, falls into the environmental wind tunnel side of things. And we know that we can see that they have some certain traits. They have no meshes, for example. So the turbulence density can be very high, as we mentioned, as we saw in figure, I think it's figure 4, where they had the power spectral density. We have a lot of turbulence. That's because there are no mesh screens, and that's for very good reason. There is very high turbulence in these impinging jets, downwards impinging jets. Also, there's no honeycomb, same sort of thing. So this wind tunnel falls into that category. So that's very good too. So we know the instrumentation and the wind tunnel themselves, they make sense. So that's in this paper, and I hope you enjoyed it. If you have any ideas of what you want us to cover in the next podcast, let us know. Otherwise, we'll stick to our schedule. We have some pretty good ones coming up. I think the next one will be about some swimming, and we have some other things after that. So make sure to like, subscribe this. And if you want to get better at theory or CFD, we have courses that you can take to get better so that you can do these things more accurately and more efficiently. If you want to make your experiments more accurate or your CFD validation data more accurate, as I mentioned in the podcast, you can check out the Atmosphere Hawk. That accurately measures the density of air by, so it drops the error from 2 to 4% to only like 0.2%, even less. And it's very easy to use. You just plug it straight into your computer, and it's very robust. And our clients all love it. So if you want to make your experiments better and your life easier, check out the Atmosphere Hawk, link in the description. And I'll see you in the next podcast. Peace out, amigos.